Imagine your job is to simulate biological life at the atomic level. To do this, computational chemists rely on standard molecular dynamics, a technique that calculates the physical movements of atoms interacting over time. The math requires integrating Newton's laws of motion in femtosecond increments, that is, 1/400,000th of a second. At that scale, you are only capturing rapid, localized atomic vibrations. But the biological events that determine if a drug actually works, like a molecule crossing a cell membrane or detaching from a receptor, take milliseconds, seconds, or even hours to unfold. This logarithmic timeline shows the massive gap in scale. Our simulation steps sit on the extreme left, while biological reality happens orders of magnitude further to the right. Because of this gap, simulations often get stuck in a metastable state. Think of it as a thermodynamic valley. A molecule stays trapped in a local equilibrium, unable to cross the high energy barrier required to unbind. If you ran a standard molecular dynamics simulation on a supercomputer and simply waited to witness a single drug unbinding event, it would require thousands of years of real-world computing time. To solve this bottleneck, scientists cannot just wait. They must mathematically cheat time using algorithms known as enhanced sampling. The first major category of enhanced sampling relies on equilibrium methods. These techniques achieve speed by directly altering the underlying physical landscape of the system. Methods like umbrella sampling or metadynamics apply biasing potentials to the simulation, essentially adding external forces to the natural environment. This energy landscape illustrates the problem. A deep valley creates a physical trap for the particle, making the mountains impassable. These algorithms fill in valleys or lower mountains. By smoothing the terrain with a biasing potential, the particle can roll across the barrier. This approach is highly effective for calculating thermodynamic affinity, determining exactly how tightly a drug binds to its target. But equilibrium methods have a fatal flaw. By artificially warping the natural forces to speed things up, we destroy the true kinetics. We lose the ability to measure how long the event naturally takes. The alternative is non-equilibrium sampling. These methods achieve speed not by changing the physical landscape, but by changing how we sample it. As this whiteboard shows, the taxonomy of these methods is dense and debated. They generally focus on two things: active forces and path sampling. In the first subset, we find active forces, specifically steered molecular dynamics, or SMD. SMD applies a simulated moving spring to literally drag an ion or molecule through a narrow biological pore or channel. A more subtle approach is random acceleration MD, or TRAMD. It was designed specifically to measure a drug's residence time. Rather than pulling along a fixed line, TRAMD applies small, randomly oriented forces to the drug. It gently nudges the molecule until it finds the organic exit pathway out of a protein pocket. This grid of binding pockets and the associated scatter plots show the result. By observing how long it takes the ligand to leave the pocket under these nudges, chemists can rank drug candidates by their relative dissociation speeds. While active force methods do not warp the energy landscape, they provide a reliable, high-throughput way to compare unbinding kinetics across a series of compounds. But the ultimate challenge is observing a passive event, like a molecule crossing a lipid membrane, without applying any artificial forces at all. This equation defines permeability, the rate at which a molecule traverses this dense lipid bilayer. Mapping this accurately requires completely unbiased dynamics. To do this, scientists use the weighted ensemble method. It is a path sampling algorithm that avoids active forces entirely. The algorithm runs thousands of standard simulations. Every time a molecule makes rare forward progress, the algorithm clones that specific trajectory, dividing its statistical weight among the new copies. Panel A illustrates this iterative cloning process. As trajectories cross into new spatial bins, they're cloned and propagated forward, while unsuccessful paths terminate. This allows the simulation to reach the other side efficiently, covering the full z-axis distance shown in Panel C. By tracking the weights of these cloned paths, scientists can stitch together a continuous, mathematically unbiased timeline of the permeation process, yielding exact kinetic data. This represents a shift in modern pharmacology. High binding affinity is no longer enough to guarantee that a drug will succeed in human trials. Real-world efficacy is driven by kinetics. how quickly a drug gets to its target, and how long it stays there to do its work. We are moving past an era of trial and error. We can now computationally map the precise, dynamic behaviors of life-saving therapeutics. Computational chemists use non-equilibrium enhanced sampling to engineer the precise behaviors of these drugs in silicon, anticipating their real-world performance years before they reach a test tube.